Hello, my name is Dmitry. I'm DevOps Data Technical Lead of JFrog. I'm very happy to participate in Citus Con conference, and I want to share my lecture about troubleshooting high CPU utilization for Postgres database. I think its topic very relevant and interesting for many specialists. Thank you. Troubleshooting high CPU utilization in Postgres databases. The only source of knowledge is experience. Albert Einstein. This presentation is based on my experience managing production business-critical systems with Postgres databases. I believe my knowledge will be useful and important. Postgres is one of the most popular databases in the world. CPU utilization is one of the critical metrics to check for Postgres database instance. Why it's important to troubleshoot the high CPU utilization in Postgres? High CPU usage is often connected to long running times, poor performance, unexpected crashes, bad end customer experience, limited scalability of applications, wrong architecture, unplanned and uncontrolled increase in cost. Checking CPU utilization allows for understanding if the database experiences performance issues, like, for example, inefficient SQL queries, lack of indexes, contention. After seeing a high CPU of the Postgres database instance, it's essential to find the root cause of the issue. Queries can be poorly written, too frequent, heavy. My presentation describes useful SQL queries and approaches that can be run on the Postgres database instance to investigate the high CPU utilization. It will also help to understand what's running in the database instance that impacts CPU usage. Database connections. One of the patterns of Postgres database leading to high CPU utilization is a high number of active connections. Connection storm is a very painful pattern for database. The following SQL query lists the total number of connections, number of non-idle connections, number of maximum available connections, connections utilization percentage. Here is an example of the SQL output. The Postgres database instance currently has 3,457 connections. The maximum number of concurrent connections to the database server is 9,057, which means 38% of connection slots are occupied. The number of non-idle connections is 3. In case the number of connections approaches the maximum number of connections value allowed for the given Postgres database instance, it's recommended to analyze application activity, review application logic, reduce the number of connections arriving to the database, tune the max connections parameter, scale up database instance. The parameter max connections defines the maximum number of concurrent connections to the database server of Postgres. Changing this parameter requires that the Postgres database instance be rebooted after a change. The new value will take effect after the reboot. It's recommended to set the max connections Postgres parameter to the maximum number of connections expected at peak load. In addition, I recommend using and tuning the connection pool, an external one like PG Balancer, an internal one like Hikari, CP for Java, or PGX for Go. On the other hand, the max connections parameter needs to be aligned with the available resources of the Postgres database machine. It should be tuned carefully to avoid system out-of-memory issues due to each Postgres database connection allocating a chunk of the shared memory and as well as non-shared memory. To tune the parameter max connections and other key Postgres database instance parameters, I recommend using free online tool like, for example, Postgres Configuration Builder that is available at the URL that you see on my screen. Distribution of non-idle connections per database. The following query allows to check the distribution of non-idle connections per database sorted in descending order. Here is an example of the SQL output. In the above example, the top non-idle sessions are running on the database MyDB1. The recommendation in such a case would be to examine running sessions of the database MyDB1 on the Postgres database instance, trying to identify long-running, badly written, and too frequent queries. Distribution of non-idle connections per database and per query. The following SQL checks the distribution of non-idle connections per database and per query, sorted in descending order as seen in the example below. Here is an example of the SQL output. In this example, the application client connected to the database 1 is running two Postgres queries. The upper query, which selects data from the table 1, has 40 non-idle connections. The recommendation in such a case would be to examine the SQL queries having the top non-idle connections. It happens that a high number of non-idle connections may appear to indicate ineffective, not scalable architecture or workload not matching the system resources. Non-idle connections detailed. The following query lists non-idle Postgres sessions that take more than 5 seconds. The result is sorted by the runtime in descending order. Here is an example of the SQL output. For each long-running query, the result set contains the corresponding runtime, process ID, database name, client address, and hostname. In some scenarios, long-running heavy queries can cause high CPU utilization. In these instances, the queries obtained in the result set should be analyzed and tuned. In case the query runs too long, causing a high load on the database CPU and other resources, you may want to terminate it explicitly. To terminate a Postgres database session by process ID, run the following command. The Postgres parameter statement timeout. The statement timeout parameter in Postgres sets the maximum allowed duration in milliseconds for any statement. The statement timeout parameter default value is 0, which means no timeout. I recommend to set a default value to at least 30 seconds at the raw session level to defend Postgres database server from long-running queries. check connections patterns in the Postgres database log files. Let's check if there is a connection storming pattern when a lot of connections arriving at the database at a specific time. This can be the root cause for a high CPU utilization of Postgres database server. Let's consider, for example, Azure database for Postgres server log files. I will demonstrate how Azure database for Postgres server log files can be parsed using awk. Awk is a text processing utility. It is very powerful and uses a simple programming language. How to list top database users by connection authorized text pattern occurrences sorted in descending order. From the output, we can conclude that the database user DB user1 did the most of connections to the database, and it can be a good candidate to investigate high CPU utilization on Postgres database server. Running frequent SQL queries. The root cause of high CPU utilization in Postgres databases may not be a necessary long-running query. Quick but too frequent queries running hundreds of times per second can cause high CPU utilization too. To find the top frequent Postgres queries, run the following SQL as shown in the example below. Here is an example of the output. The result set indicates a list of queries and corresponding frequency, how many times each query runs per second. Recommendation: examine SQL queries and corresponding application logic. Try to improve the application architecture to use caching mechanism. This will help to prevent the running SQL queries too frequently on the Postgres database server. Check execution plan of the queries. It's important to examine execution plan of the running queries. Here we can see explain plan of some query that selecting count 1 from my table according to some criteria. And we can see here function apps. From this explain plan, we can see high cost, high execution time, sequential scan, and no indexes used. Here's an example of explain plan that retrieving data from some table, and we can see here again high cost, high buffer shed hit, and we can see that actually this query returns just one row. That may be indication of bloat in the table or vacuum process that didn't run on this table. The Postgres parameter random page cost. Reducing the parameter random page cost value relative to the parameter sec page cost will cause the system to prefer index scans. Default value for the parameter random page cost is 4. My recommendation, in case you are using SSD storage, to lower the parameter random page cost to 1. Invalid indexes. One of the reasons of high CPU utilization may be missing or invalid indexes. The following query checks invalid indexes. In case invalid indexes found, they should be rebuilt and/or recreated. Reusing cached prepare statements flow. In case accessing Postgres via JDBC driver using a prepare statement cache, it can be performance degradation and high CPU utilization. During the first 5 executions of the prepared statement, Postgres engine is using good execution plan. However, starting from the 6th execution, it will use generic execution plan, which will lead to performance degradation and high CPU utilization effect. Recommendation: disable prepared statement caching. Postgres database server CPU distribution by queries databases. The following SQL checks how much each query in each database uses the CPU. It provides a result set sorted by the most CPU-intensive queries in descending order. Here's an example of SQL output. From the output example, you can see the first query select from the table 1 takes the most portion of the CPU because of a high number of calls. I recommend looking at how often the application is running queries connected to this Postgres database. Also, from the output example, you can see a high mean time of the second query, which is retrieving data from the table 2. We can see here that mean time exceeding 3 seconds, which is a lot. Postgres database statistics. Outdated Postgres statistics can be another root cause for high CPU utilization. When statistical data is not updated, Postgres Query Planner may generate non-effective execution plans for queries, which will lead to a bad performance of the entire Postgres database server. To check the last date and time the statistics were updated for each table in the Postgres database server for a specific database, connect to the database and run the following query. Here is an example of the SQL output. Recommendation: ensure tables are analyzed regularly. To collect statistics manually for a specific table and its associated indexes, run the following command. Postgres database bloat. In cases of intensive data updates, both with frequent update and with insert-delete operations, Postgres tables and their indexes become bloated. Bloat refers to disk space that was allocated by a table or index and is now available for use by the database, but has not been reclaimed. Because of this bloat, the performance of the Postgres database server is degraded, which can lead to high CPU utilization scenarios. Under a normal Postgres operations, tuples rows that are deleted or stale because of an update aren't physically removed from the table. They are stored there until the vacuum command is issued. Vacuum releases the space occupied by dead tuples. It's necessary to perform a vacuum periodically, especially for tables that change often. To check information about dead tuples and when vacuum auto-vacuum was run for each table for a specific database, connect to the database and run the following query. Here is an example of SQL output. It indicates the number of inserted, updated, deleted, and live tuples per table since the last time the analyze process was performed. Continue of the previous SQL output. It indicates the last date and time the vacuum auto-vacuum process was performed. Recommendation: ensure tables are vacuumed regularly. To run vacuum for a specific table and all its associated indexes, run the following command. Vacuum can be run by an auto-vacuum process together with statistics collection. Auto-vacuum is a background process that executes vacuum and analyze commands automatically. To collect database statistics and to do vacuum on all the objects of all the databases, run the following command. To collect database statistics and to do vacuum on all the objects of the specific database, run the following command. Proactive Postgres database scanner. On mission-critical systems, it's important to be proactive in preventing the situation that the key parameters of the system, including CPU utilization, reach maximum values that directly impact performance, stability, and cost. Like in medicine, we want to find a cure as soon as the first symptoms appear. I'd like to consider an approach that makes it easy to identify queries that use the system inefficiently, help to find a root cause of the performance issues, assist to understand typical workload patterns and performance bottlenecks. The found patterns and queries can be improved and system will work efficiently. The proactive Postgres database performance scanner is a script that connects to a database and runs a set of probes that can be extended if desired. All the probes are queries to a database that are unified by structure. It includes the threshold value, description of the check, the issue this check is associated, recommendation on how to troubleshoot the issue, SQL query to perform the check, an additional optional SQL query in case there is a need for more evidence. If some check exceeds the threshold value, then the corresponding report will be generated in the following standard format: description of the check, date, time, environment details, the issue, details about the issue, additional evidence, recommendation. If there are several Postgres databases that need to be monitored, the proactive Postgres database performance scanner can be run in the loop. Example of how to run the proactive Postgres database performance scanner. Example of the output of proactive Postgres database performance scanner. Here we can see check according to the table pgstat statements, the database queries that take more than 5 seconds. Another example of the output of proactive Postgres database performance scanner, you can see the queries that occupy more than 10% of CPU. The source code of the proactive Postgres database scanner can be found by URL that you see on my screen. Conclusion. In this presentation, I examined the most comprehensive and effective troubleshooting practices for high CPU utilization issues in Postgres databases. I believe this knowledge will become part of the playbook for any production mission-critical Postgres database environment. Thank you very much.